This presentation will provide a brief overview of the geospatial data science field. First, we will discuss some guiding principles for the vast field of data science. Then we will turn to the geospatial niche, discuss the data lifecycle, evaluate important contributions from applied geography, look at critical expertise, skills, and tools, and finally wrap up with some applications of geospatial data science. Data science has many definitions and subdisciplines. Regardless of the variety, data science intrinsically involves the informed use of data to guide human understanding. The field has been rapidly evolving over the past few decades with the introduction of new technologies, expanding storage, and increased processing capacities. By its nature, the field is interdisciplinary and relies on domain expertise alongside certain guiding principles which are rather consistently relevant. Data scientists are computer scientists, statisticians, geographers, and more. Let's look at some guiding principles that generally apply across the board. Ethics must be continuously evaluated when embarking upon any data science project. Many codes of ethics exist, and it can be helpful to have a distilled code to assess at various project stages. For example, a custom code of ethics for guiding my own work has been more than 20 comprehensive considerations organized into 5 themes: do no harm, maintain integrity, improve society, perpetuate truth, and ensure quality. From informing epidemiological public health decisions to smart city infrastructure and beyond, managing data as a critical asset is important to a strong community. Data always has limitations that must be considered. Tools are inspector gadgeted together to work towards goals. Professionals have specific specialties and strengths. Understanding the strengths, weaknesses of data, tools, and professionals is important. In a world inundated with data and data sources, selecting the appropriate data for a specific project can mean the difference between affecting positive change to spreading information. Rely on data and topic experts to guide data selection. A goal may be to explore an observed pattern and gain a better understanding. It could also be to identify appropriate solutions to a problem. Regardless of the established goals, keeping them in sight leads to better solutions and consequently results. Always check the work. Find other experts to review processes, evaluate logical assumptions, and consider the contextualization of results. This is really important. Clear documentation increases the value of work and helps the processes developed find additional applications beyond the extent of the project for which they were developed. If data and knowledge just sit in the mind of a data scientist, that is a disservice to the work done and the people which it might benefit. Know the audience that needs to be reached, and with the goals still in mind, identify the best formats for disseminating content on a project-by-project basis. Data science has many subsets and niches, including geospatial data science. Spatial data, commonly geographic, contains information about where data is relevant and the relations to other spatial data. We can overlay many layers as seen in the image on this slide. Geography itself is interdisciplinary, as is data science. Each field integrates well with one another, as well as other fields like community planning. Geospatial data scientists can fill many roles in numerous domains. One might find them looking for correlations between related data, identifying statistical inference to inform next steps, determining geographic suitability for an initiative, providing compelling visualizations, and identifying strategic solutions for moving forward. They look through a geographic lens to inform understandings of patterns, and we'll look a little bit more about contributions from applied geography here in a minute. When viewing data through this lens, unique insights may be revealed with numerous applications. Data life cycles come in many formats. The cycle I am presenting here lends itself well to geospatial data. In the stage of goal orientation, topic experts and stakeholders discuss what the needs are, how they might arrive at solutions, and what applications those will have. In data preparation, it is important to involve data experts for identifying appropriate sources and processing that data accurately for next steps. When transforming data into knowledge, a geospatial data scientist must evaluate and ensure the validity of the data, integrate that content with other information, create models, and perform analysis. The impact of the work up until this stage may be null unless the content is disseminated in an effective format. This may involve summarizing key points, providing context to place the information, visualizing, and applying the results to satisfy the initial goals. Finally, in the wrap-up stage, data may require operational maintenance and find additional purposes beyond the scope of the initial project. When the time is right, archiving and purging is best practice. Theories can help explain processes, patterns, phenomena, and data, and help make the predictions as well as propose solutions to problems. The field of applied geography has many specific considerations that should be taken into account. Here are just a few of those. Tobler's law says that everything is related to everything else, but near things are more related than distant things. This may seem obvious, but it has huge implications. Further, the related assumptions are challenged by globalization and technology of the 21st century. When data has both coordinates identifying the spatial location and an indication of time, the results can become even more meaningful. For example, crop damage, maybe from a frost, on different sites of a farm over a specific time might propose predictions as to how one might increase crop yields in the future by planting in one location or taking a specific approach to covering the crops. Where we draw the lines is very important, and that brings us to the modifiable areal unit problem. So for example, if you consider the population density of a neighborhood compared to the population of that same neighborhood plus adjacent commercial areas, you're going to get different population densities, and that has an effect. So depending on the project you're doing, you want to consider where those lines are going to go. Having a representative sample is the only way to have valid data. For example, if you ask residents to complete a survey about their neighborhood, but only the individuals over a certain age complete the survey, that data is not representative of the resident experience in that neighborhood. How a map is projected can greatly influence the interpretation of results. A map projection takes the lumpy cylinder that is our Earth and attempts to preserve certain features like area, shape, and distance. But there are always compromises of some variable, or all of them to a certain degree. On this slide, we see two different projections, one in the background and one in the foreground. That one in the foreground with the triangular angles is one of my favorites, called a Dymaxion. It does a nice job of preserving shape and area. All data is an approximation. It is dependent upon collection methods, preparation, representative sample, and more. I hear people discredit data as an approximation, but that's really a fallacy. Statisticians and demographers, data scientists can approximate using well-tested and reviewed methods much better than one single human brain can speculate. But we must consider that it is still an approximation, as is everything in this world, really, and it can be accurate to the goals in the area that we're pursuing. I mentioned it before, but I'm going to mention it again. Ethical considerations are really important. Geospatial data science has some unique ethical considerations that must not be overlooked. For example, historical redlining has had detrimental impacts on who could purchase a home and where. All these considerations and more are important to keep at the forefront of our minds as geospatial data scientists embark upon projects and move through the data lifecycle. So what expertise, skills, and tools are important for a geospatial data scientist? That depends on the project. Domain expertise is always important to some degree. A geospatial data scientist must have topic expertise in both geography and data science. That's non-negotiable. But they also benefit by having some degree of topical knowledge specific to the project or access to collaborate with topic experts. Depending on the goals of the project, different skills will be more critical. Most projects will involve visualization, analysis, and documentation. Specific projects may require other hard skills like data management or machine learning. Soft skills should not be overlooked. Collaboration is often essential. Ability to innovate and problem solve are huge assets to one's skills. Project management, whether over oneself or over a strategic team, can ensure project success. The fields of data science and geography have both been rapidly evolving, as we've mentioned. With that, there are more options than ever for GIS tools, including proprietary options like Esri, open source options like QGIS and the Leaflet API, and hybrid scalable options like Mapbox and Carto as well. The possibilities for applications are nearly limitless. Combining map layers and CSV data sources overlaid in coordinate space and contextualized with topic expertise transforms data into knowledge. By garnering more knowledge about the world around us, we can better understand our communities. When seeking solutions to problems, geospatial data science provides unique abilities to visualize meaningful results. Those results can often reveal unique geospatial insights that would have otherwise been obscured. Opportunities can be uncovered and pursued to improve our world and our subcommunities. By better understanding reality, decisions and policy changes are better informed, more accurately communicated, and inevitably more effective. All of these items lend themselves to curating solutions for real-world problems. And these are just a handful of the nearly limitless applications in geospatial data science. So that wraps up this overview of geospatial data science. This presentation was prepared and recorded solely by me, Weaver, in October 2020. To learn more, you can check out my website at www.lwellweaver.com. And all images used in this presentation are attributed to the Creative Commons. Thank you.